Hi, welcome to this week's lecture. Today we're actually going to first wrap up on what we have discussed so far in the course. So we have basically talked about processes and threads, CPU scheduling, synchronization and deadlocks. And these were like the previous topics that we covered. This week we are going to talk about memory management. Also next week, and the week after we are going to talk. The third week in April we are going to talk about file systems and I/O storage. So let us go back to what we discussed a while ago about how memory is accessed by the different programs in using the operating systems. So let us start by a bit of history. In the early days, the case was that you would run the operating system and a single program with the operating system in memory. If you lived in the old days when computers were called IBM compatible, like there was a company that was called Tandy, and there were many of these very small companies. Many of them died now. Memory back then was more like 64 kbs. I mean, on many computers, I had a computer that actually had, I think, 32 kbs of memory, which is nothing basically. It's a Word file. So back in the days, you did not really have the option to multiplex multiple computer programs at the same time in memory. So what early operating systems did was that you would run the operating system and one single program in memory. And back then, operating systems were not even, the operating system of these days was DOS, which I believe some of you might have seen. So it was very lightweight. There were no Windows. Windows started actually in the 90s. So in this case, no abstraction is given to the program. Addresses are physical, so you're accessing, since you have the operating system having reserved memory, and then whatever is left is basically just for the process. So addresses were physical, and there was only one program running at a time, so there was no overlapping of CPU and I/O, which basically meant that multiplexing was much harder. So if you had a program running, then it almost owned the whole computer. You couldn't basically, for example, have multiple windows. There were no windows back then. And the way you would basically sort of get a program out to load another program while not shutting the first program was via swapping. And swapping was basically saving the state of the program to disk. Then after you save this, you start loading another program into physical memory and run it. Can you think why is this not efficient? Yes, as you probably guessed, it's basically because disk access is very, very slow. So when memory sizes started to basically get larger, when you started getting like 512 kbs of memory, these were like, this was like an advancement that people were like, yeah, we have half a meg of memory. So basically back then people started thinking about, well, we might need better multiplexing. And swapping is inefficient since you have to go and load the files from disk. So let us load multiple processes into memory at the same time and multiplex between them. Now, if you do that, you need to provide some form of protection between the different processes, because you don't want process B to access process C's memory. This memory can be sensitive data. It can be like your password or something, but also it can corrupt other processes. So if process B is able to access memory of process C, it can corrupt process C, even non-intentionally. So a bug in process B can corrupt process C. So this is why you started having the need of much better protection on your computer systems. And until this day, this is basically a lot of security issues are basically in computer systems just arise because of the way we multiplex multiple processes in memory at the same time. So processes basically try to read memories of other processes, malicious processes. So what you need if you have multiple programs sharing memory, you need three things. First of all, transparency. Second is protection, and the third is efficiency. Transparency is basically that the operating system gives the process the feeling that it's the only process running on the memory. So no process should be aware of that the memory is shared or how the memory is shared. Okay. And a process, when you write a program, you do not basically assume that this program will be stored on this line in RAM, for example, in memory. You just compile it, and then the operating system magically puts it somewhere, and the program should run no matter where you are in this memory. So if process B switches its place with process C, you should still have both of them running with no issues. So you shouldn't have any notion of where you run in memory. Protection. So processes must not be able to corrupt each other, as we said. And above all, they should not be able to access the operating system memory, because now multiple processes are residing with the operating system on the same physical memory. And you want the performance of CPU and memory to be efficient, and you shouldn't have much degradation due to this sharing. So these are the main three traits that you would want in a program on a shared memory machine. So now the way that we do that is that by having address spaces as an abstraction. So each process does not see all of the memory and does not even see what physical memory it runs on. Instead, the operating system provides a process with an abstraction that basically provides it with a virtual memory. Okay, and the virtual memory is basically a virtual address space that the operating system creates. Okay, and this is basically what we are going to study this lecture and the next lecture. How do you basically provide this abstraction, this virtual memory space to the process? Okay, the code, heap, and stack, all of them will live on top of this abstraction for a program. So the program code, the heap, and the stack are running they think they are running on the real memory. They are actually stored on the real memory, but they do not know the address. So if you try to get the address of a process, the memory address of a process, via the process, not via the kernel, you will get a virtual address.